This is a short presentation where I'm going to go through the solution to workbook question 6.5 from the FEEG1003 thermofluids module. So here's the question. It's about a new technology, heat pumps. Two types we tend to use, air source and ground source. And you'll be aware that a heat pump, we use work to move heat from one place to another. So the question, again, reading the question, there's no diagrams or anything, so we've got to tease out the relevant information. So the first one is electric heating, and this is something you'll come across possibly in your second year when you move out of halls into residential housing. And this is electric heating is very popular with landlords for a number of reasons. But you're asked what is wrong thermodynamically using electric to heat houses. I can go through this one verbally right now. Electric heating, incredibly cheap. So if you have a wet heating system, so you've got a boiler and then pipes running through the house, feeding radiators. Standard condensing boiler, probably install cost between £2,000 to £3,000, and obviously the maintenance associated with that. It's a condensing boiler nowadays in the UK. If you replace an old boiler, it has to be replaced with a new condensing type, and these are quite complex pieces of equipment. So again, you have annual maintenance. Something goes wrong with a wet heating system, got cold and hot water running around the house, so you can have leaks. Electric heating, by contrast, is incredibly simple. It's just an electrical resistance heater. Individual units are incredibly cheap, fairly robust. If they break, very easy to replace again. So commercially they make perfect sense for a landlord. It means their costs are reduced. However, your costs will be increased. So electric heater, 100% efficient. So for every unit of energy that goes in, it gets converted straight into heat. Thermodynamically, what's wrong? That electricity comes from usually a process that involves heat. So that electricity is generated at, should we say, 33% efficiency for a standard coal-fired power station, using a standard Rankine cycle. About 38% efficient from a nuclear station, again using a Rankine cycle, and about 65% efficient for a combined cycle gas turbine. But all of those stations have quite high losses, thermodynamic losses of heat. So the upshot is that your electricity will cost you around about 16 pence per kilowatt hour. That's a UK domestic charge at the time of making this presentation in 2015. So 16 pence per kilowatt hour. That will be 100% efficient going into your electrical heating system. If you have a condensing gas boiler, that's going to be about 95% efficient, 92 to 95. But the cost of gas is only 4 pence per kilowatt hour, so a quarter of the cost. So that means that if we account for, call the boiler even 80% efficient, that means that it's 16 pence per unit of heating versus 5 pence per unit of heating. So it's much more expensive to heat your house electrically than it is with a wet gas-fired heating system. Okay, so obviously if you move out of halls, it would be nice if you could find a house with a decent gas boiler. They have to have safety certificates done annually, I believe, nowadays. So if you can get one with a wet heating system, your costs will be reduced. And as students, you're here for the coldest part of the year. You usually leave us in May, just as the heating season is finished, and then you come back in October, just about before it starts. So you are here for the coldest part of the year. On the flip side, you will divide all your bills by 4 or 5 people, so you won't feel the full cost of heating your house as such. It will be divided by a number of people, so that sort of reduces the financial burden on you. Okay, part B. So now we've got a house that's heated by electric heaters. We are given you've got 10 kilowatts installed, electric heating. That's not very much. So a standard UK house might be 20 to 40 kilowatts, maybe heating demand. Maybe this is a student house where you've got 2 jumpers on and it's a bit a bit colder. Actually no, because it says the inside temperature is 20 degrees. So you've got a highly insulated student house, which I find unlikely. An outdoor temperature at -5. And what we're going to do now is propose to replace electric heaters with a heat pump. Okay, so this is the equation that defines a heat pump. So we're actually getting more heat out per unit of work put in. And this is the key part here. I'll elaborate this on it in a little bit, but again, this heat pump is electrically driven. So this heating system is still driven electrically, but it's a heat pump. So we're hoping that for every 1 unit of work we put in, we'll get multiple units of heat out. And that's kind of what the coefficient of performance is, this ratio. There's 2 types, ground source and air source. Ground source heat pump. There is actually one in building 37, the student services building on main campus. As you go in the main sliding doors, there's a silver grate just to the right hand side as you go in, and that's actually the vent, the extract vent for a heat pump. Electric motor, or driving a pump, and that pumps circulates air around coils that are buried in the ground. So in the UK, if you dig down about 1 metre, 1.5 metres, the temperature down there is about 15 degrees all year round because it's nice and thermally insulated. So what you can do with these sort of systems, and they're very good for commercial buildings, is when the air temperature in winter is below 15 degrees, you can draw in air from your heat pump at 15 degrees, so it's partially heated, and then you can give it a bit of a boost. In summer, when it's very hot outside, you can draw in this 15 degree Celsius air from the heat pump system and use it for cooling. So they can work in both directions. So they're very good for in climates with sort of reasonable temperature swings either side of this stable temperature below the ground. We can also have air source heat pumps. They're less efficient because you have issues with water condensing and freezing and things like that. So they have slightly higher electrical sort of ratings for the same units of heat delivered. But we can assume this one's a ground source heat pump anyway. So what we're doing is in the winter, so we're -5 degrees outside our house. So what we're going to do is turn on the heat pump, and that will draw in air that is 15 degrees Celsius, and then we just have to give it a little boost up to 20. So thermodynamically, it makes a lot more sense. And we're given the price of electricity, 7.5 pence per kilowatt hour. So again, this is by way of an example. Present cost is about 16. And finally, one key part of information that I've just missed. It has a coefficient of performance 20% of that of a reversible one. So a reversible heat pump is based on the equivalent sort of the coefficient of performance, the equivalent equation to Carnot's efficiency. You'll recall that COP is a flipped value, so we get numbers greater than 1, hopefully, if it works well. Right, and we're given 4 questions now. We've done part A, so part B, we've got the cost of the original electrical heating in pence per hour, the COP of the proposed heat pump, so we can work out the reversible coefficient of performance, and then the actual, and the power input it requires, and then how the running costs compare. And then finally some practical things. How would you decide whether to replace the electrical heaters with a heat pump? So considering all of these factors. And I guess the key one here that's not listed is probably the installation, the install cost. I guess that is rolled into the purchase and the loan. But we'll cover that one as well. So over to the board now to solve this. Right, we're now going to solve this part of the question, part B. Drawn here standard heat pump diagram. So notice the arrows, work going in, and we're moving heat from cold to hot reservoir. Let's plug in the numbers. Our cold reservoir is at -5 degrees. -5 degrees Celsius, convert straight to Kelvin. So 268. And our hot reservoir is at 20 degrees So this is the internal temperature of our house. So 293, and we're moving 10 kilowatts of heat. Okay, so that's a standard diagram, everything obeying both the first and second law of thermodynamics. Very quickly, the electrical heating, quite easy, so 10 kilowatts, 7.5 pence per kilowatt hour. So electric is 75 pence per hour. Okay. Again, if you're heating a house for 8 or 9 hours, 10 hours a day, all this will add up. Okay. Right, so on to the heat pump, the coefficient of performance. Our standard equation, and again this is kind of flipped, so we had a heat engine. This would be a squiggly N, and we'd have our network divided by our hot heat. But it's flipped over for coefficient of performance. And as this is a heat pump, we're doing heating, not cooling. So this is not like question 6.4 where we had a refrigerator. That's going to be QH. And we can rewrite that. Minus QC. What we can do then is substitute temperatures instead of heats. Again, this is fully reversible. So assuming all the heat flow is expressed in a change in temperature. So we've got our values in Kelvin. So our reversible COP is 293 divided by 293 minus 268. Gives us a value of 11.7. So according to the reversible performance, for every 1 unit of work that we put in, we get 11.7 units of heat, which is very, very good. However, we're then told in the question our actual heat pump has a COP of 20%, that of the full reversible system. So the real COP equals 11.7 times 0.2, which equals 2.34. Okay. Now if we work out the work that goes in, okay. So this gives the value in kilowatts. Rearranging this equation, you get 10 kilowatts divided by our COP, 2.34, and that equals 4.26 kilowatts. Okay. So now we multiply that up. Just check the costs. Yep. So that so 7.5 pence per kilowatt hour times 4.26 kilowatts gives us 32 pence per hour to heat, so considerably cheaper than our electrical heating system, which we would expect. Now where heat pumps fall down, especially in the UK where we've got a big difference between these two numbers, is this. So in the UK, electricity is approximately 16 pence per kilowatt hour. Gas, as I said, alluded to before, is approximately 4 pence per kilowatt hour. Okay, electrical heating 100% efficient, gas-fired wet systems possibly 95% efficient. So let's just take these two values as they are, leave them the same. That means that because we're going to use an electrically driven heat pump, we need a coefficient of performance that is greater than 16 divided by 4. The COP has got to be greater than 4 for this to work. Okay, and you can see for this one, the coefficient of performance was 2.34. Okay, so well below 4. So it means the additional energy we need to boost the heat up, to provide heat for the home, it's going to mean our heat pump's not going to be particularly good. If you go online and look at standard manufacturers, they all claim coefficients of performance of about approximately 4, pretty much spot on. So that's really borderline in terms of the coefficient of performance and this differential between gas and electricity. And this will stay relatively constant because due to this cost, electrical cost, our electricity comes from many different sources: coal, gas, nuclear, renewables, so they all contribute to this price. But whilst it remains 4 times or more expensive than gas, then the gas is always going to win really for your heating system domestically. Part 4 of Part B of this question talked about discussing the different types of system. Well, electrical heating, as I said before, is incredibly simple, it's cheap, it's reliable. So again, landlords tend to favour it because their tenants aren't playing around with gas as well. So you tend to get electrical hobs, induction systems, for example. So there just needs to be no gas in the house at all. So from a maintenance point of view and gas safety, that's all bypassed by the landlord. So very helpful for them, higher cost for the tenants. Ground source heat pumps, there was one, as I said, in building 37. It makes perfect sense during the construction phase of any building project to put in ground source heat pumps because you're already excavating the land for foundations and the like, so you've offset that the major cost, which is laying the pipes underground and then covering them back again. That's most of the installed cost will be that. And the actual system itself is incredibly basic. Electrical motor, a pump, control system, round in a loop. So most of the cost is the excavating and burying the cable again. So to retrofit a heat pump, you're unlikely to see payback within a lifetime of the system because you're paying that extra amount to bring excavators on site and lay and install the system. But if you can share that cost with the general construction of a building or a house, domestic property, it makes a lot more sense. And then the payback times with the renewable heat incentive in the UK are reasonably favourable, so you can see payback within, say, 10 years or so on average. But again, not necessarily a quick win. Okay, so hopefully discussed a bit about thermodynamics there and a bit about the practicalities of these different systems and given you some solid advice when you move out of halls and into your student houses next year.